The world of modern physics is built upon two monumental pillars, quantum mechanics and Einstein's theory of relativity. Together, these theories laid the groundwork for many of the technological advancements we take for granted today, from lasers and GPS to the rise of quantum computers. But perhaps the most profound shift is occurring at the intersection of these theories, thanks to breakthroughs in the field of quantum computing. For decades, black holes have stood as some of the greatest enigmas in physics, massive cosmic entities with gravitational forces so powerful that nothing, not even light, can escape their grasp. Their interiors, often referred to as singularities, represent points of infinite density where our current understanding of physics seems to break down. For years, these mysterious regions have been the focus of intense speculation, but no one could truly explain what happens inside a black hole. That is, until quantum computers entered the scene. Now, thanks to the extraordinary computational power of quantum systems, scientists are beginning to peel back the layers of these cosmic giants like never before. What they're discovering is fundamentally rewriting the laws of physics. No longer are black holes seen as simple cosmic vacuum cleaners that swallow all information forever. Instead, quantum mechanics suggests that information, the very building block of reality itself, cannot simply vanish. And quantum computers are helping us find answers to one of the most perplexing mysteries of the universe, the black hole information paradox. For over 50 years, physicists have been grappling with the idea that information that falls into a black hole is lost forever, a concept that contradicts the core tenets of quantum theory. This paradox stems from the very fabric of black holes, long believed to be one-way streets for matter, light, and even time itself. But what if that's not the case? What if black holes don't destroy information, but instead store and transform it? This revolutionary idea begins with a mind-bending concept called holography, the notion that black holes aren't three-dimensional objects at all. Instead, they could be two-dimensional surfaces that store and encode information, like a cosmic hard drive. This radical perspective, known as the holographic principle, suggests that everything inside a black hole, every particle, every piece of information, is not contained within the black hole's interior but is actually encoded on its surface. The only problem. Proving this was an almost impossible task, until now. Classical computers simply weren't powerful enough to simulate these extreme conditions and test this hypothesis. But quantum computers, with their ability to handle vast numbers of interacting quantum states at once, have made it possible. These extraordinary machines can simulate microscopic black holes and even model their behavior in ways that were previously unimaginable, revealing some astonishing new insights. Rather than swallowing information and erasing it forever, quantum simulations suggest that black holes may actually scramble this information, encoding it in the very radiation they emit. This new understanding could provide the long-sought resolution to the black hole information paradox. But the story doesn't stop there. For decades, physicists have been caught between two seemingly incompatible theories, general relativity, which governs the universe on large scales, and quantum mechanics, which rules the subatomic realm. Black holes, born from the collapse of massive stars, exist in a space where both theories should apply, but neither theory fully explains their inner workings. General relativity predicts that inside black holes, gravity becomes so intense that it forms a singularity, a point of infinite density where the laws of physics break down. Quantum mechanics, on the other hand, insists that information cannot be lost or destroyed. This creates a fundamental clash. If matter falls into a black hole and is lost to the singularity, it contradicts quantum theory's principle of unitarity, that information is never destroyed. This became known as the black hole information paradox. For decades, physicists have been trying to reconcile these two ideas, with some proposing that black holes slowly leak energy via Hawking radiation, a process where black holes evaporate over time. But the critical question remained, where does the information go? Is it truly lost forever, or does it somehow escape? Classical computers, despite their vast power, were far too limited to answer these questions. The calculations required to model black hole dynamics involved billions of quantum states interacting simultaneously, an intractable problem for traditional machines. But now, quantum computers operating not with binary bits but with qubits, quantum bits that can exist in superposition, are giving us a new way forward. These qubits can represent multiple possibilities simultaneously, allowing quantum computers to solve problems that would otherwise take longer than the age of the universe to compute. Recent breakthroughs have enabled scientists to simulate small-scale black hole analogs, unlocking new insights into the behavior of black holes. The findings have been extraordinary. Rather than losing information forever, black holes appear to scramble and eventually release it. The dynamics of information flow within black holes are more complex than previously imagined, but the crucial point is that information doesn't disappear, it gets encoded in the Hawking radiation emitted by the black hole. One of the most exciting applications of these quantum breakthroughs involves the study of wormholes, hypothetical tunnels, through space-time that could connect distant regions of the universe. For years, these enigmatic structures were considered mere theoretical curiosities. But now, quantum simulations suggest that entangled black holes could function like wormholes, providing a potential method for instantaneous information transfer across vast distances. This could provide the first real evidence of quantum teleportation on a cosmic scale. Physicists have long speculated that black holes and wormholes might be two sides of the same coin, with their deep connection rooted in the fundamental nature of quantum entanglement. The famous ER=EPR conjecture, proposed by Juan Maldacena and Leonard Susskind, suggests that Einstein-Rosen bridges, wormholes, and quantum entanglement, EPR pairs, are essentially different manifestations of the same underlying phenomenon. If this is true, it means that black holes may not be isolated cosmic prisons but rather interconnected portals to other regions of spacetime, potentially even other universes. This idea, while speculative, has gained some support through recent quantum experiments. By creating quantum circuits that mimic the entanglement patterns seen in black holes, researchers have observed behaviors consistent with wormhole-like information transfer, providing tantalizing hints that we may be on the brink of understanding black holes in an entirely new way. In the not-too-distant future, powerful quantum computers could even enable us to decode the information encoded in Hawking radiation, effectively allowing us to peer inside black holes. This would be a groundbreaking achievement, providing us with answers about the origins of the universe, the nature of time, and perhaps even the possibility of multiverses. In a more profound sense, the quantum mechanics behind black holes might also reveal deep truths about the nature of reality itself. If black holes are indeed quantum computers, processing and storing vast amounts of information, it suggests that the very fabric of space and time might be emerging from quantum information. This has enormous implications for our understanding of everything, from the fundamental laws of physics to the deepest philosophical questions about the nature of consciousness and existence. As quantum computing technology continues to advance, we will be able to explore these cosmic mysteries with increasing precision. The future of black hole research is on the verge of transforming our understanding of the universe. We are no longer just trying to understand the extreme environments inside black holes.